Hello, this is Mark Case from Lehigh Carbon Community College Science and Motion program. And today we're going to be taking a look at a kinetics experiment to study the rate of which a dye called crystal violet is going to fade in color over time when we add some sodium hydroxide to it. Your teacher will be sharing with you the lab procedure, as you can see on your screen, which is taking a look at a very complex organic molecule. Those little circles that you have inside of a hexagon, those are called benzene rings, which are six carbon atoms that are sharing three double bonds between them. So you have these three benzene rings that are hooked on to another carbon that link them together. And notice that that central carbon has a plus charge on it. When you add hydroxide to it, the OH minus charge will be able to link up to that carbon, and then it will change the geometry, because now instead of having three areas of charge, which is a trigonal planar shape in terms of the original structure with the C plus, now with four areas of charge around it, it's going to be more of a tetrahedral arrangement around the carbon. This changes the color of light that is absorbed, and it goes from a purplish color to one in which you're going to end up dealing with a colorless solution. A much more simplified equation is just showing crystal violet with a plus sign, a plus charge on it. That's the purple color. And adding the hydroxide, which is a clear liquid, is going to go to a colorless form of the crystal violet with the OH attached. The equipment that we're going to be using is using a spectrophotometer. Basically, we're going to be studying the rate law of the reaction. And the way you figure out the rate of a particular reaction is that there's some constant, the rate law constant, a proportionality constant, based on how quickly the concentrations changing affects the rate of the reaction. We take the crystal violet's molarity, which is symbolized by having them in brackets, raised to a power. In this case, it's M. That's called the rate order in terms of the crystal violet. And the hydroxide is raised to an nth power. These two exponents, these powers that you have as the rate orders, have to be determined experimentally. And you do that by changing the concentration of one of the two of the reactants, either the crystal violet or the hydroxide, and then see what effect it has on the rate. If you change the concentration so that you end up where you're say you double the concentration of the crystal violet, if you have no effect on the rate, then usually that indicates it's probably a zero order reaction. So crystal violet raised to a zero power is equivalent to one. It doesn't affect how fast the rate occurs. If you take that crystal violet and you double it, and the rate also doubles, then that would be a first order reaction. If you take that crystal violet and you double its concentration, and the rate ends up being squared two times that concentration, then that's a second order reaction. So we look at it as either a zero, first, or second order. You can also determine that graphically by taking a look at the amount of absorbance in your spectrophotometer, which is proportional to your concentration, and see how that changes over time. So that's what we're going to focus on. How does it change over time? Um, if you see that the absorbance versus time is basically going to be a linear plot, that means that even though the concentration is being used up as the reaction occurs of the purple crystal violet plus sign, that means it has no effect on the rate of the reaction. If you take a natural log of the absorbance, which indirectly is like taking the natural log of the concentration, it's proportional to that versus time. If that is a linear relationship, a linear plot, then it's a first order. And then if you look at it where the inverse, 1 over the absorbance value versus time, is a linear plot, that usually indicates a second order reaction. That also helps you determine what the rate constant, the K value, is for that setup, because that's tied into the slope of whichever line gives you a straight line relationship, either absorbance versus time, linear, natural log versus absorbance versus time, or 1 over absorbance versus time. The materials that we're going to be using and the objectives, you can look at that more as you have your lab procedure in front of you. The equipment that we're going to be using, you could either be using a colorimeter, which has only certain wavelengths from an LED light source, or we're going to use a full range spectrophotometer to take a look at how this will work. To get set up and started, let me just take a look at using the SpectraViz and how to set that up itself. So with that, we're going to jump over and take a look at using the GoDirect SpectraViz Plus. So you see on your screen now that over here on the left-hand side is the GoDirect SpectraViz. And when we open what's called Vernier Spectral Analysis app, it can let us measure absorbance or percent transmittance, or you can also have it create its own light. There's 2 light sources inside that will excite the particular solution that you have and maybe cause it to give off its own glow, or you can do emission tests like with elements. So we're going to look at kinetics, absorbance versus time. So I'm going to click on that to start that experiment. Now, usually it's going to take about 90 seconds to warm up, but I have my SpectraViz already plugged in. So it's basically only just needs a quick warm up. I'm going to be placing into the chamber a cuvette. Now, these cuvettes basically have ribbed edges. That's the sides you want to handle them on. And then the other part is clear. That's where the light source is going to pass through. You don't want to put your fingers on that clear side because even your fingerprints can actually scatter the light and then give you a greater absorbance than it should be. So I put that down inside so that the light source is passing through. I'm going to finish the calibration. It's going to take a reading on that and then basically get an idea of what that value is. And it's canceling out any absorbance of the water as my solution, and also any absorbance by that plastic cuvette. Next, what I'm going to do is I'm going to take some that have this purple colored crystal violet in it. This is my standard. It's 2.5 times 10 to the negative fifth molar. So as far as a sample goes, that's very dilute. It's not a very high concentration. But with dyes, biological stains, they have a tendency to have a very deep, rich color. So I'm put this inside here, and you'll notice that my curve is actually sort of spiking here above an absorbance of 1.5. Normally, we would want to have a concentration so we don't go above 1, because this absorbance relationship relative to concentration is tied into a natural log relationship. So it's actually a logarithmic scale that we're looking at here. And we start losing direct linearity between the absorbance and the concentration if your absorbance values exceed 1. But in this case, we're going to be causing the color to fade and disappear, so it's okay to start at a higher value. If I click, about where I think the peak is, sort of the middle of that curve, I want to use a wavelength maybe of around 570. You can be, either side of that. It doesn't really matter. So I could go anywhere from, about 516 up to about 624. I'm just going to pick somewhere in the middle here where I'm, sort of at the peak, and then say done. So what it has set up here is it's reading what the absorbance value is at a wavelength of 572 nanometers at its maximum peak. And you can see that on the little insert on your screen. Now, what I'm going to do with this is I'm going to take 10 milliliters of the crystal violet. Let me take out this cuvette and get a empty cuvette that I'm going to be using here momentarily. And what I'm going to do is I'm going to add 10 milliliters of the 0.1 molar sodium hydroxide. You might notice that 0.1 molar is much stronger and much higher concentration than 2.5 times 10 to the negative fifth molar for the crystal violet. So there's lots of excess sodium hydroxide. Let me dump that in. I'm going to use just a disposable pipette to quickly suck that up and down a couple times. And let me put that inside of my cuvette so that it's 3/4 full. You want to get it about 3/4 full because the bottom half or so is where the light source is passing through. I'm putting the cap on it just so that we don't have any spillage. Place that down inside, and now you can see I'm already down at 0.6. So it's adjusting, it's about 0.9. I'm going to start collecting data. Now it's going to take a reading every 2 seconds. And because it's not taking a reading every second or every half second, it might be a little jittery in the beginning here as far as your absorption values, but it is going down and showing a relationship where it's starting to drop fairly quickly. I can slide this over just a little bit. Come on there. I want you to be able to see the data as it's being plotted. There we go. So we started out, 8.85, somewhere in that area as our peak, almost 0.9, and now we're dropping pretty quickly. We're all the way down to 0.6, and that's in roughly, less than a minute. Now this will run for maybe about 3 minutes or so until this fades to a point where it's going to be very light. And you might be able to notice that over here, we're getting some of the same fading. It's going to be losing some of its color intensity as it works its way into the reacting of the sodium hydroxide with the crystal violet. And this will eventually start to level off at some particular point. Now, initially, it looks fairly linear. It's tough to say because we have a relatively small sample set so far. I can zoom in on this if I want to. If I double click somewhere on the graph, it will expand that data. And you can see up here where we started at to where we are now, this little curve down the bottom compared to the original curve, we're under 0.4 absorbance at this point. I'm going to close this insert just so it's not in our view. And then I'm going to double click on the graph, which will auto scale it to the data that's actually being displayed at this point. So we've just hit a little over 2 minutes and we're down to about 0.3. Now here's where it's going to begin to slow down the rate of the reaction. The reaction rate is dependent upon the collisions of the particles of the crystal violet with the hydroxide. They have to align themselves in the right position so that that OH group can get in there next to that carbon plus and bind to it. So the 3 benzene rings that are around there in a way are sort of obstructing with that reaction. As the concentration decreases, there are fewer particles that have the carbon with a plus still remaining on it, and therefore there's not as many collisions that could form a bond between the C plus and the OH minus. So that's one of the reasons why the rate is slowing down. The rate in any time frame could be determined by just taking a look at the distance between the y-axis, the absorbance, over a period of time. So if we looked at, say, the first 100 seconds, a rough estimation is that it went from about 0.85 down to a value of about 0.4, and that was in 100 seconds. You could calculate the absorbance versus time for that value. If this stayed linear all the way through, well, then that would mean that it would be zero order. But because we're looking at a change here that it's not linear all the way through, and if we run this for about 3 minutes to 4 minutes, somewhere in that time frame, I'm going to keep waiting until I get down to a little below 0.1. We can then do our analysis and figure out what is the relationship that we have between the natural log of absorbance versus time, and also between the inverse 1 over absorbance versus time.